Hi everyone, and welcome to the example video for section 7.1. So we're going to be showing some examples of the application of integration by parts, and we're going to try to show in each example why we choose the u and the dv that we do. So remember that the formula we're going to be applying over and over again here is the integral of u dv is equal to uv minus the integral of v du. So it's sort of like a sophisticated substitution type system. The first example we're going to start with is this function. Now, when you're looking at a function and you think to yourself, this is integration by parts, one of the things that you're looking for is a piece that if you let it be u and you took its derivative, then it would disappear or become simpler. And so this is about the most straightforward idea you can get when you're looking at integration by parts, because this t right here, if you let u be t, and you took its derivative, t turns into 1. That's a much simpler function than t is, especially in an integration formula. And I also know how to take the integral of e to the minus 5t. So I'm going to be doing this by parts, and I'm going to let u be equal to the part that's going to disappear, which is t, and I'm going to let dv be everything else that's left over as long as I can integrate it. Now notice that du is just dt, because the derivative of t is 1. On the other hand, dv, when I integrate it, turns into minus 1/5 of e to the minus 5t. So this comes from the formula that anytime that you have an integral of e to the anything t, that's equal to 1 over k e to the kt. Okay. So 1 over -5 is minus 1/5. You can show that rule using u substitution if you're interested, but this is also in the table of integrals that you should have available to you, and one that you should be recognizing with lots of practice. So let's apply the formula to this, and we're going to get, well, this integral is uv minus the integral of v du, and hopefully what we get here is some integral of v du that's an easy integral. uv is minus 1/5 t e to the minus 5t. And then the integral of v du, well, there's v and there's du, so if I multiply those things together, I get minus 1/5 e to the minus 5t dt. And that's an integral I know how to do. So I get minus 1/5 t e to the minus 5t plus 1/5 integral of e to the minus 5t dt. And using the same idea I used over here, I can write minus 1/5 t e to the minus 5t, and this turns into minus 1 over 25 e to the minus 5t plus c. A very typical application of this rule. The next example we're going to look at is one where it's not going to be so clear how else we could even do the problem. So in the video that we made for the theory, we talked about the example of the integral of the natural log. This is in that family. Let's look at the integral of the inverse sine. Now I know the derivative of the inverse sine. I know that d by dx of the arc sine is equal to 1 over the square root of 1 minus x squared, but I don't know its integral. So this is one of those problems where if there's no other way to proceed, one thing that you can do is, well, I've got no idea what's happening, so I'm just going to hope that if I let u be equal to the thing I'm trying to integrate, and dv just be dx, that I can replace this integral with an integral that I can actually solve. So du is 1 over the square root of 1 minus x squared dx, and v is just x. Well, look what happens. Using the formula uv minus the integral of v du, you get x times the arc sine of x minus the integral of these functions multiplied together, but you've made a u substitution. You can use u substitution on this integral, because if you let u be equal to 1 plus x squared, that's du. So the first step was to use integration by parts to change this integral into something that we can use regular old u substitution on. Let u equal 1 minus x squared, so that du is equal to negative 2x dx. And after you do the substitution, what you're going to get is that all of this is equal to x inverse sine of x minus the integral. Okay, so this gets replaced with a minus 1/2 du, and on bottom you have a square root of u. Well, that's easy, because this is just x arc sine of x plus 1/2 times the integral of u to the minus 1/2 du, which is x sine inverse of x plus, okay, so the antiderivative of minus 1/2 is u to the positive 1/2, and I could divide by 1/2, which is 2. So you get u to the 1/2 plus c. But u was equal to 1 minus x squared, and so the final answer here is x arcsine of x plus 1 minus x squared to the 1/2 plus c. Now that might seem like just a cluster of math here, right? There's lots of things that we did, but this is the sort of blend of ideas that comes up in more sophisticated anti-differentiation problems. Anti-differentiation is hard, and a lot of functions that we'd really like to know their antiderivatives, you have to use technique like this to get it. So again, this was a two-step problem. Step 1 was about reducing it to an integral I could use u substitution on, and that was this step. So that's the part we used integration by parts up here. Once we had an integral we could use u substitution on, a second technique, the u sub technique, lets us go from here to the final antiderivative right here. As a third example, let's look at a function where we're going to get the original integral back again and have to solve for it. So it doesn't really matter what you choose for u or what you choose for dv in these problems, as long as you're consistent about it from step to step. So what I'm going to do is I'm going to always let the u's be the e's, and the dv's will be whatever the trig functions are. So u is equal to e to the 2 theta, and dv is the sine of 3 theta d theta. You could work in x if you want to. You don't have to work in theta. Same exact idea, though. So du is 2e to the 2 theta, and v is minus 1/3 cosine of 3 theta. The formula says that I'm supposed to take this and replace it with uv minus the integral of v du. Plugging in, if I take u times v, I get minus 1/3 e to the 2 theta cosine of 3 theta. And then this integral is 2 times minus 1/3 is minus 2/3. I get an e to the 2 theta and a cosine of 3 theta d theta. And if I really want to, I can pull all of the 2/3 out front, although it doesn't really matter so much. Now I'm not done, because this integral, I'm hoping to get a copy of my original integral back again. This is one of those algebraic ones where I'm going to solve for the integral in the end. And I'm not done yet. So I'm going to use integration by parts again. So let's let u be equal to minus 2/3 of e to the 2 theta, because I can put the 2/3 wherever I want. So I'm going to stick it in with the exponential. And I'll let dv be equal to the cosine of 3 theta d theta. Then du is equal to minus 4/3 e to the 2 theta, and v is equal to 1/3 sine of 3 theta. Using the same formula from before, the uv minus the integral of v du, I can write this as minus 1/3 e to the 2 theta cosine of 3 theta minus this integral is all going to get replaced with uv minus the integral of v du. So I'm going to get minus 2/9 e to the 2 theta sine of 3 theta. That's uv. So this part is u times v from here, u and v. And I'm going to multiply these guys together to get v du. And that's going to give me minus the integral of minus 4/9 e to the 2 theta sine of 3 theta d theta. Now this is a jumbled mess right now. So what I'm going to do is I'm going to take this equation and I'm going to rewrite it again so that it's clearer. So first I'll write it at the bottom, and then we'll continue our computation on the next slide. So this is where we're at. So this integral right here, I'm calling I. That's I. I is equal to minus 1/3 e 2 theta cosine 3 theta plus 2/9 e 2 theta sine 3 theta plus 4/9 of I. Because this integral right here, this guy, that's just a constant times I. The original integral was e to the 2 theta sine 3 theta. This integral is e to the 2 theta sine of 3 theta. So everything we've written down here turns into this algebraic expression right here. There's an I on the left-hand side, which is equal to this. which is equal to this, which is equal to this, and this is all equal to this right-hand side, which also has an I in it. And so this is the equation that I'm going to solve. And what I'm going to end up with is, well, subtracting 4/9 I from both sides gets me 5/9 of an I. And the last step is just to get the 5/9 over to this side. So I is equal to 9/5 times all this stuff. And that's it. You're done. There's your antiderivative. Don't algebraically simplify this at all. So these tend to be a little messier than the other ones because you have to do the thing where you do twice and then do algebra at the end. But they're also pretty easy to recognize because we're in the case where I know that this function here is going to keep having the same sorts of derivatives, and this will have a pattern where it goes sine, cosine, sine, cosine, sine, cosine. So eventually we're going to end up with the same integral back again that we started with, times some other number, but the actual integral is the same. For the last example, I want to show you something I call the table method, which is a way of doing repeated integration by parts very quickly. And the observation here that we're going to make is when we were doing integration by parts with the u and the dv, we always did u and du and dv and v. And how did we, when we had these quantities, what did we do with the formula? When we multiplied these two together, and then we subtracted the product of these two. So this sort of straight across line is going to represent an integral, but there was no integral when we did a product diagonally. And so I can actually compute all of the derivatives and integrals I need in a big table and then just glue it all back together again with multiplication and alternating addition and subtraction. Now, why alternating? Because this was uv, and there was a minus sign stuck to this because we did minus the integral of v du. And if we had to do integration by parts again, that negative would apply to the formula uv minus v du, and so you'd have a negative and a positive on the next integral. So here's what the table method looks like. Pick the thing that you know will disappear. So in this case, I know that if I take the derivative of t to the third enough times, it's going to turn into a 0. So do that. So for the u column, you have t to the third, 3t squared, 6t, 6, and 0. And as soon as you get the 0, that's where you know how to stop. Okay? I need integrals to go down the other side. So dv. So cosine of 2x. Here you're going to have to know your integration. The integral of the cosine is the sine, but because I had a 2 inside, it's going to be 1/2 of the sine of 2x. And if you don't believe me, take the derivative of 1/2 times the sine of 2x and see that you get cosine of 2x back again. Integrate again, and you're going to get minus 1/4 cosine of 2x because the integral of sine is negative cosine. Integrate again, and you're going to get minus 1/8 sine of 2x. Integrate again, and you're going to get positive 1/16 times the cosine of 2x. And it's positive because the integral of sine is negative cosine, so you get two negatives and they cancel each other out. The last thing we need to do is glue this stuff all together with repeated applications of the integration by parts formula. So this is a uv. And this is a uv for the next integral. And this is the uv for the next integral. And this is the uv for the last integral. And I know it must be the last one because there's a 0 right here. So the integral of 0 is a constant. So uv just means I'm going to multiply and multiply and multiply and multiply all the way down. In the first formula, it was uv minus the integral of v du. So this is going to be plus, and this is going to be minus. For the next integral, it's got to be plus because a negative applied to a negative is a positive. And alternating down the lines. So the solution is just 1/2 t to the third sine of 2x. That's these two things multiplied. Minus 1/4 times 3t squared cosine of 2x. So notice here, if we wanted to, we could have simplified these numbers into a single number by writing instead positive 3/4, I think. Now I'm going to multiply these guys together. That's the third one. And I'm going to get, well, 6 times, it's positive, and 6 times negative 1/8 is minus 6/8 t sine of 2t. These are supposed to be t's all through here. And finally, the last step has got a negative in front, and it's 6 over 16. And so that is the answer. So all we did here was build out this table where we took a derivative down this column, we took integrals down this one, and then we went uv minus uv plus uv minus uv plus uv minus uv until we were finished, because we got this 0 down here and we don't have to go any further. Now you'd imagine the table makes things like this much easier, because otherwise you're going to have to do 4 different integrals by parts, and that's going to take forever. So once you get your basic integration technique down, the table method is a very fast way of doing this. And if you're clever, I will leave it to you to figure out if there's a way that you can take this idea of doing it in tables and applying it to these big nasty problems like we solved last time. It turns out there's a way to apply the table here, but I don't want to show you because that's like giving you a weapon that I haven't taught you how to use. All right, work hard.